Let us try to plot all the diagonals of this given polygon here, and let us try to name each one of them. Take note that a diagonal is a line segment connecting any two non-consecutive vertices. For this given figure, specifically a hexagon, we can draw here diagonals. But how many are they? The number of diagonals is given. Let me just use here a thicker line. Let us use the diag, not just d, so that it could actually not be differentiated by distance and and other notations. It is given by the formula n times n minus 3 all over 2. Now, as for how this formula came to be, we could actually spend time for that later. It would actually take us a lot of analysis, but as of this practice exercise is concerned, let us just use this formula to determine the number of diagonals for this given figure. Since this is a hexagon, n here is 6. It has 6 sides. So the number of diagonals is given to be 6 times 6 minus 3 all over 2. So we have 6 times 3 all over 2. That is actually 6 times 3, 18 divided by 2, which is 9. Or 6 divided by 2, 3 times 3 will also be giving us with 9. So this is the total number of diagonals that we could actually draw for this hexagon here. And what are those diagonals? Let us try to draw them one by one, and let us try to check if there are really 9 diagonals here. To draw a diagonal again, simply pick a vertex. Let us use point P, as it is the first letter here in the alphabet P. So we are going to use this one, and let us draw a line segment from point P to any of the vertices as long as it's non-consecutive to point P. If we say non-consecutive, point Q and T, or vertices, vertex Q and vertex T are not anymore possible. So we could jump here and draw this line segment here. And this is now diagonal. The name for this is diagonal. Again, it's a line segment, so it has this notation, diagonal PS or diagonal SP. Right? The next set of diagonals is from vertex P to vertex V. So we have here the name for this is P, V, and line segment, or VP and line segment. And finally, the last line segment that could be drawn from vertex P is going towards R, and the name for that is line segment or diagonal PR or RP. Again, Q and T are exempted because vertices Q and T are the consecutive vertices of vertex P. The next diagonals should start with another vertex. Take note that we still have 6 more as we only gave 3. So let us start with this vertex here, Q, and let's connect it with any of the non-consecutive vertices. As vertex S and P are consecutive, or the vertices which are consecutive to vertex Q, so they are exempted. So the next line segment is from Q to V, and this is actually line segment or diagonal QV or VQ. The next would be from Q to R, and this is called to be QR or RQ line segment. And then we have here QT. Right? This is Q, and we have here T. So we have 3 diagonals from point Q or vertex Q that we could draw in this given hexagon. So we have here 6 already. So given in this formula we have solved earlier, we only have three more diagonals. And let's try to determine what are they. Let us use another color here. Let me use here color orange. So since we are done with P and we are also done with Q, let's proceed with S. Some of you might say SP, sir, okay? Because I could actually draw here S and then P. But line segment or diagonal PS earlier uses the same vertices. Take note that in the previous figure, without this line segment, a colored orange line segment, it is already a line segment, a green colored line segment connecting points S and P. That would mean let us not duplicate it. We could not duplicate it anymore because if we are going to again write here SP, they mean the same thing. And the number of diagonals here are called to be the unique diagonals. Okay, so let us remove that. And instead of connecting S and P, let us connect S and R. Okay, so before that, okay, let us have a short review. S and P cannot anymore be connected because it was already connected earlier. Vertex V and vertex Q are not possible for vertex S because they are consecutive vertices. So the next would be SR. So it's line segment or diagonal SR. Okay. And then the next would be S and then T. So you have here the line segment S and T or TS. And then no need for SP because they already connected earlier. So we only have two for this. No need to duplicate the third one. So we have 1, 2, 3, 4, 5, 6, 7, 8. We still have one more. And what line segment is that, or what diagonal is that? Let's continue with the color pink here. So we will have we are not going to start with V. So if we talk about vertex V, vertex R and S are not anymore possible because they are the consecutive vertices to vertex V. VQ is already given by QV and VP is already given by PV. That would mean we can only connect vertex V to vertex T, and that is actually vertex VT or TV. Again, we only have this. As for these are already connected, and so on and so forth. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have now reached the number of diagonals we have solved earlier for irregular or a hexagon. Let us try to determine if there are no more diagonals here as we move to vertex R. If we go to vertex R, we cannot connect it with T or nor V because they are the consecutive vertices. And we cannot also connect it with S because we already have SR earlier. RQ is already given by QR, and then RP is already given by PR. In short, no more diagonals can be drawn from this vertex. And then if we're going to proceed with T as our last vertex so that we could complete our rotation here, no need to connect with P and R because they are the consecutive vertices. TV is already given by VT, PS is already given by ST, and TQ is already given by QT. Now that we have exhausted all vertices, we have determined that the number of diagonals being 9 is already correct, and these are their names. They are line segments, therefore we use the notation for line segments. So if we are going to have a different type of polygon, let's say pentagon, let's say heptagon, or the other ones, the bigger ones, we have dodecagon, tridecagon, we could also try to draw them. Okay. But if the question is just how many, the number of diagonals, you could just simply end in this process. But I just simply added here the continuation to list all diagonals so that we could actually demonstrate here how the diagonals should be written and to make sure that no diagonals should be duplicated as we count them. This is the last video for this lesson, and we will have more videos soon, so please stay tuned. Goodbye.